Okay, good afternoon, everyone. I hope you guys had a good Thanksgiving break and ready for the last 3 weeks of classes, and then the long Christmas break. So today we're going to talk two ideas. The first one to take us the first 15 minutes, which is the idea of coordinate with respect to a basis. And after that, we're going to start the last chapter in the course, eigenvectors and eigenvalue, which is absolutely crucial for you. So first we start with the notion of coordinate with respect to a basis, and which is section 2.9. Right. So definition, and then we do examples. So let H be a subspace of Rn. And again, to help you think about it, H could be, if you think about subspace of R3, it means H could be all of R3, a plane through the origin in R3, or a line through R3. That's to help you kind of figure out when I'm talking about a subspace. And let B, V1 through Vk, a basis for H. Let's remember what it means. It means all the vectors are linearly independent, and it means that the span is H. It means those vectors are linearly independent, and those vectors cover all of H. And let X be a vector in the subspace. Then, the definition. The coordinate of X with respect to the basis B. So imagine R3, and I have a bunch of basis vectors, and I pick any vector in R3. Then the coordinate of X with respect to the basis are nothing more than the weight C1 through Ck, such that X is C1 V1 plus C2 V2 plus Ck Vk. So if H is a subspace, it means H is the span of V1 through Vk. I pick a vector in here, it means it's in the span. Then the coordinate of X with respect to the basis are nothing more than the weight that gives me X as a linear combination of the V1 through Vk. And we use the following notation for the coordinate with respect to a basis. So X, B represent the basis. So the coordinate of X with respect to B are C1 through Ck, are those weight. And this reads the coordinate of X relative to the basis B is C1 through Ck. Okay. Note that the entry of the coordinate depends on the order of the vectors in the base. So if I order them, V1, V2 through Vk, C1 is the weight I put on V1, C2, the weight I put on V2, etc., Ck, the weight I put on Vk. Okay, so that's the definition, and let's do two examples. So definition is actually simple. Now let's do examples along those lines. So example number 1. Can I remove the paper? Okay. So example number 1. Okay. Suppose I take R2 as my subspace. So let H to be R2. That's my subspace, and we know it's a subspace. And I'm going to take the following two vectors. So let B be equal to. So the following two vectors. 1, 2, and minus 1, 1. Okay. Now, first, let us note that B, this is a basis for R2. That's a basis for R2 because the two vectors, 1, 2, and minus 1, 1, are linearly independent. Just by looking at them, they are not scalar multiple of each other. And we know that in R2, any two vectors, any two linearly independent vectors span R2. Okay, so this is the basis for R2. Now, let X be the following vector. Let X be equal to 1, 5. And the question is, find the coordinate of X with respect to the basis B. Okay, find the coordinate of x with respect to the basis b. First, algebraically, what does this mean? And then geometrically, what does this mean? So first, algebraically, find the coordinate. What does this mean? It means the following. Let me read the definition. Suppose b is a basis. Then the coordinate of x with respect to the basis are the weight that will help me to write x as a linear combination of the element of the basis. So find the coordinate, it means that we need to find the weight. To find the weight C1 and C2 such that, that's what it means, find the coordinate. I'm gonna call this V1 and this is V2. So such that x equal C1 V1 plus C2 V2. So find the coordinate with respect to a basis, it means find the weight. Now this is type of problem that we've done actually a lot. So this is really equivalent to solve the following system. So V1, it means 1, 2, and V2 is minus 1, 1, and X is 1, 5. It's really boiling down to solve this system for C1 and C2. So we go to the echelon form and we solve this system. And we get the following. We get actually 1, minus 1, 0, minus 2, minus 3, 1. And this is minus 2 plus that, which is going to give me a 3. So this means that C2 minus 3C2 equal 3 equal minus 1. And C1 is 1 plus C2. It means that's a plus 3 in here. 1 plus C2, which is equal to 2, which tells me that the vector x could be written 2v1 plus v2. So what's the coordinate of x with respect to the basis? It means the coordinate of x with respect to the basis are those weight. It's 2 and 1. That's what we call the coordinate with respect to the basis. So 2 and 1. 2, it means 2v1 plus v2. So that's fairly simple, something we have done. And geometrically, what are we doing? The geometry is simple, and then why people care about those ideas. So geometrically, that's the picture. I have the vector v1, which is 1, 2. I have the vector v2, which is minus 1 and 1. And I have my vector x here. So my vector x here is 5, sorry, it's 1, 5. What does it mean to find the coordinate of x with respect to the basis v1 and v2? Let us remember something from the coordinate system. Let me take you back to the coordinate system. Since you guys were basically in middle school, what did we do? If you take any point xy here, what does the coordinate xy mean? Xy means that you need to go x unit in this direction to get to the point and y unit in this direction. So it means that xy is, as we said, x e1 plus x y e2. It means x and y are the coordinate of the point xy with respect to what we call the natural basis, e1 and e2. That's what x and y is. Now the question is, why we have to take e1? Why do we need to express every vectors in terms of e1 and e2? So the question here is the following. You don't need e1 and e2 all the time. You can use any two linearly independent vector and use them as your new coordinate system. So I'm going to use v1 as a new coordinate. So instead of using the x1, x2 as my coordinate, this is telling you can use any vector as your coordinate system. So I'm going to use the vector, the line carrying v1, carrying v2 as my new coordinate system. And if I pick any vector in x, finding the coordinate of x with respect to v1 and v2, it means asking the following. If you want to go from 0 to x, how many units you have to go in the direction of v1 and how many units you have to go in the direction of v2? And we've seen before that, if you have two linearly independent vectors, any vectors, you can reach it by going into v1 and v2. So this is telling me that you need 2 units in the direction of v1 and 1 unit in the direction of e2. Okay, so the idea is the following. A lot of times, instead of using the x1, x2 as your coordinate system, you can use any 2 vectors as a new coordinate system. And this is depend on the problem you're dealing. And the coordinate of x with respect to b, to 1, is telling you that with respect to this new coordinate system, so that's my system now, the vector x, which is the vector 1, 5, is 2, 1 in this new coordinate system. It means you go 2 units in direction of v1 and 1 unit in the direction of v2. So that's the idea of the coordinate with respect to a basis. I'm changing my point of view. Instead of using this as a coordinate, I'm using this new thing as my coordinate system. Okay. So question number 2. So question number A, let x be 1, 5. Find the coordinate of x with respect to b. It means find the weight. Question number 2, to basically understand this a little bit more. Suppose that x be in R2, be a vector in R2. You're given that xb, trying to understand the notation, you're giving that xb equal, for example, 5, 6. Okay, and the question is find x. Okay, so what does this question mean? B is the basis I took originally. So B is the same basis, 1, 2, minus 1, 1. And if I tell you the coordinate of x with respect to xp is 5, 6, what is x? What does this notation mean? This notation means that the vector x is the 5 and the 6 represent the weight I put on 1, 2, and minus 1, 1 to get the x. So this notation means that my vector x is 5 times 1, 2 plus 6 times minus 1, 1. Okay, so that's what this notation means. So the coordinate of x with respect to the basis is 5, 6. It means to get to x, I need 5 units in the direction of v1, and I need 6 units in the direction of minus 1, 1. And that's the notation we use. And this is all the idea of changing our coordinate system. Okay. Now I take one more example, and then we move on to eigenvectors and eigenvalues. So example number 2 is the following. All right. Let me take, I'm very sorry about that. Roger, pick up the phone. Sorry, I didn't know that the phone is next to me. Example number 2 is the following. Let me take H to be the span of the following 2 vectors. Three, 4, 2. Okay, so we have 2 vectors in R3. So right now I am in R3. And H is their span. It means basically I have those 2 vectors, 1, 1, 0, 3, 4, 2. Those are my vectors. And I'm taking every possible linear combination of them. It means I'm taking basically, geometrically, I'm taking the plane containing 0, 0, 1, 1, 0, and 3, 4, 2. Okay. Now, a basis for R2. Suppose I take B, consists of the following vector. Those. This is form a basis for H. Because those two vectors are linearly independent and H is their span. So by definition of basis, those form a basis for R2. Now the question is the following. Let X be equal to 5, 6, 2. That's my X. And the question is, show that X is in H and find the coordinate of X with respect to the basis B. Okay, so basically it's the same idea. My H now in subspace, which is a plane, and I have a vector X. I'm asking you to show that X is in H, means in the span, and find its coordinate with respect to the basis. Means basically I want the vector X somewhere, and I want to ask you the question, find the coordinate. It means if you want to go from 0 to X, following 1, 1, 0, and 3, 4, 2, how many units you have to go in each direction. So I'm writing X as a linear combination, and those weight will be called the coordinate of X with respect to the basis B. So let's do that. So X is in H. So it means that we have to show that X is in the span of my two vectors and find the weight. Find the weight. Right. So the problem is, again, I have two vectors, so I need to solve. X is C1 times this plus C2 times that. So this is 1, 1, 0, 3, 4, 2. We have to solve this. And my vector is 5, 6, 2. So again, I need to set up the system. And remember, here I have only 2 unknown, not 3. I have only C1 and C2. Having 3 equation does not mean I'm going to have a C3 free. I don't have, I only have 2. So we solve this, and we solve it. And we get the following. Unless I'm doing a stupid mistake, we get that. 0, 1, 1. Again, when you solve, you have to get to the echelon form. If you don't get to the echelon form, your solution is not correct. So you have to keep going till you get to the echelon form. So this is going to give me, now we solve. Remember, we have only 2 unknown, not 3. Having this row doesn't mean you have another unknown. Give me that. This first will read C2 equal to 1. And this line will read that C1 is 5 minus 3 is equal to 2. Means my vector X is 2 times 1, 1, 0 plus 1 times 3, 4, 2. Means the coordinate of my vector X with respect to the basis B is 2, 1. Remember, I have only 2 coordinates here because I have 2 coordinates because I have 2 basis vectors. So the number of coordinates here are the number of the vector inside the basis. So be very careful. X as a vector in R3 has 3 components as a vector in R3. But as a vector in the plane, the coordinate with respect to B are 2 of them because they represent, we have 2 vector bases. Each one of them is the weight that I put on the base. So geometrically, basically what we are doing is what we've been doing. That's the geometry of it. I have the vector 1, 1, 0. I have the vector 3, 4, 2. And I have the plane that's obtained by both of them. And the way now I'm thinking about this problem is like this. I'm basically forgetting a little bit R3. And I'm only focusing on the plane. And I'm putting a coordinate system on the plane. How are we putting the coordinate system? We're going to take this coordinate system that consists of the line containing 110 and the line containing 342. So this is my really coordinate system right there. So this is a plane and this is my coordinate system. And the idea is that I'm taking a vector in H and I'm writing it as a linear combination of those two vectors. In other words, this vector is in H, in the plane, in this plane P, that's my H. I'm asking myself, if I want to go from here to here, how many units I go along 110 and how many units I go along 301. And the idea that you have to go 2 units here, 1 unit here. So 2 and 1, we call them the coordinate of the vector x with respect to the spaces. And the idea of putting coordinate system in a plane have a specific name. We are coordinatizing the plane. It means we're creating a coordinate system on the plane in R3. Okay? So that's really the idea of coordinate with respect to a basis. I can do that also for R3. Instead of expressing every vector in R3 as a linear combination of the E1, E2, and E3, the idea is you don't have to pick E1, E2, E3 as a coordinate system. Any 3 linearly independent vectors can be used to create a coordinate system on R3. And sometimes the physics of the problem requires a coordinate system, which is not the regular one, E1, E2, E3. So we can use any 3 linearly independent vectors in R3 to coordinatize R3, to express every vector as a linear combination. Right. So this is the idea of a coordinate with respect to a basis, which is actually, of course, all those ideas are very much used. Now we're going to move to, as I said, the last chapter in this course, an extremely important chapter, and this is chapter 5. Chapter 4, you know, a lot of pieces in chapter 4 have been covered in 2.7 and 2.8, but in a little bit more generality that we don't actually need. So we're moving to the last chapter in this book, section 5.1, 5.2. Eigenvectors and eigenvalues. So I'll write them down. Eigenvectors, eigenvectors, and eigenvalues. Values, it's a number, vector is a vector. All right. First definition. I will read it and then I do problems by itself. First definition. Let A be a n by n matrix. So we have a matrix. An eigenvector of A. An eigenvector of A is a non-zero vector x. It's a non-zero vector that has the following property, that when A acts on it, it stretches it. It means if A times x is a certain scalar lambda times x. So a vector x is called an eigenvector if the action of A on it is to stretch it. Means AX is a lambda x for some scalar lambda. So the picture is of an eigenvector is the following. Suppose A is a matrix. That's a vector x. It's called an eigenvector if when A acts on it, it means when you take A times x, its effect is to stretch it. It takes x and stretch it by a factor lambda. This scalar lambda by which A will stretch the vector is called eigenvalue. So a very simple example tells you to understand this definition. So suppose I take the following. So let's write this down. Suppose I take A to be equal to 3, that's the matrix, a 2 by 2 matrix, minus 2 and 0. That's 3. And I'm going to take V to be to 1 and W to be the vector to 0. Question number A. Is V an eigenvector? An eigenvector for A. So what does it mean? Eigenvector. V is an eigenvector if A times V, if A stretches V by a scalar. That's when an eigenvector means take the vector V and stretch it. So how to verify that? So it means the question is A V equal to lambda V? I mean, does stretch it? So to check that, we just take A and we multiply it by the vector V and ask ourselves, does it stretch it or not? All right, so it's just a multiplication. So we take that and we multiply it. And we see what we get. So if we multiply, we're going to get 3 times 2 is 6, 6 minus 2, that's a 4, and a 2. And the question is it equal? Is this a scalar times V? As simple as that. And the answer is this vector a scalar times V? That's the definition. Okay, 4 times 2, I can definitely write it as 2 times 2, 1. Okay, so A times V is equal to 2 times V. Means if this is my vector 2, 1, when I apply A to it, A will take it and stretch it by factor of 2. That's A times 2, 1. And that's exactly the definition of an eigenvector. So it means V is an eigenvector. And 2 is called the eigenvalue. Now I know that the idea seems very strange, eigenvectors, but their application, we will see definitely an application in class, they come up everywhere. I mean, they really come up almost everywhere in physics, in differential equation, in a lot of your courses. Now B, let me take the vector W. Is it an eigenvector? Okay, I don't know. I take A, multiply it by W. And I ask myself, okay, does A stretches W or it doesn't? So let me take W to be 2, 0, and that's 3 minus 2, 1, 0. So I multiply them. I ask myself, do we stretch it? 3 times 2 is 6, 2. And the question is this equal to a scalar times 2, 0? That's really what's an eigenvector. So that's A times W. Can I write this as a scalar times W? And of course, no. There is no way I can find the scalar. So W is not an eigenvector. Not an eigenvector. Okay, so that's the definition of eigenvector of a matrix. It's a vector that the matrix stretch. It takes it and stretches it. So they're very specific vectors. And a matrix does not stretch every vector. Like this is a matrix A. It did stretch A times V. That's its action on V, but it didn't do that for the vector W. So it doesn't do it for every vector. So the problem that we have to face is basically, we have to answer today is actually the following. How to find those eigenvectors. I mean, how to find them. Now I gave them to you. There is no eigen. Okay. So the question is how to find those eigenvectors in general and how to find those eigenvalues. What it turns out is the following. To be able to find those eigenvectors, I first have to find those lambdas. So it's kind of backwards. So to find them, I need to find the lambdas, the eigenvalues. Once I find those eigenvalues, I will be able to find the eigenvectors. So the big question of this section today is how to find those two, how to find this vector V. And to do that, I need to define eigenvalues a second time in a more systematic way that will help us solve the problem. If it isn't an eigenvector, then absolutely no eigenvalue, no eigenvalue. If it's not an eigenvector, there is no eigenvalue. End of the problem, absolutely. Okay, so now here's my question. To be able to find the eigenvectors, I will have to find first those, and then I can find the eigenvectors. So my question now, not my question, what I'm gonna do now is give another definition for eigenvalues, which will allow me to find the eigenvectors. And here is our definition. So I read it, and then I will work with it. So definition. If you guys are writing, I will keep it for a little bit. Let A be n by n matrix. A scalar lambda is called an eigenvalue if the equation ax equal lambda x has a non-zero solution. So let's read it very carefully. A scalar lambda is an eigenvalue if I can find a non-zero vector x such that ax equal lambda x. This non-zero vector that I can find, the non-zero solution, will be called the eigenvector of A that correspond to lambda. So I keep it so you guys read it again. So suppose A is n by n. A scalar is an eigenvalue if I can find a solution for ax equal lambda x. And I can find this vector x such that ax will stretch by lambda. This vector x that I can find will be called the eigenvectors of A because x, A is gonna stretch it. So let us analyze this. Here I have a matrix A, 1, 6, 5, 2. And my question is, show that lambda equals 7 is an eigenvalue. What does this mean? And how we're gonna show it. So now I'm gonna take, this is gonna be the most important part of the lecture here, but that's how you're gonna understand the whole concept in a way. So this is my matrix A. And my question is, so in the first problem, I asked you to show that this is an eigenvector. This is unchanging. So my question is, show that lambda equal to 7 is an eigenvalue. That's the first part. That's me. What does this mean? Show it as an eigenvalue. It means I have to show you that I can find a vector x, not 0, such that ax is equal to 7 times x. So I have to convince you that there is a non-zero x, such that ax equals 7x. So let's write this down. Let's write this down. It means show that lambda equals 7 is an eigenvalue. It means we need to show the following, that the equation ax equal 7 times x has a non-zero solution. A non-zero solution. Okay, we know what A is. That's A. So we want to show that I can find x so that ax equals 7x as a non-zero solution. And the problem is how to solve this. I mean, how can I solve ax equals 7x? So far, we've solved a problem like this. We solved ax equal to 0. We solved ax equal to b. But b was a constant vector. And this was the unknown vector. But now I have the x from both sides. I want to say ax equals 7x. We've never really done something like that. So what we're going to do is do the following. I'm going to subtract 7x from both sides. I want to somehow collect the x's. So this is equivalent to solve ax minus, so that's equivalent to show that this equal to 0 has a non-zero solution. Every step is important right now. Now I need to solve this equation. Again, I have a problem. How can I solve it? Somehow I would like to factor out the x. But how can I factor out the x? How can I factor out the x? Let me ask you a question before I do the math. Ax equal, I want to factor out the x. Tell me if what I'm writing makes sense. Can I do that? Yes or no? I would like to factor out the x because I want to create a homogeneous system out of the system I have. So I have ax equals 7x, ax minus 7x equal to 0. I'm going to create something that I can work with. So the question is, can I factor the x this way? Yes, no. Okay, anybody else? Yes, anybody else? Anybody else? Anybody else? Okay, I see a lot of yeses, but the answer is no. Why no? Because 7 is not a matrix. Absolutely correct. From here to here, that's not correct. A is a matrix. 7 is not a matrix. So this absolutely not legitimate as an operation. So I cannot do that. So I'm trying to factor out the x. So because if I'm solving, suppose I tell you solve 5x minus 2x equal to 0. So the first thing you guys do is recombine those, giving you 3x equal to 0. And I'm trying to imitate this. I'm trying somehow to imitate it, but I cannot take a minus 7 because a minus 7 is not really a legitimate operation. That's a matrix and that's a number. So I cannot do that. So what is the trick to go around this? And here is what we're going to do. I'm going to rewrite 7. We're going to rewrite 7x as follows. Okay. 7 times. Instead of x, I'm going to rewrite x as the identity times x. And this is correct. Anything times x will give me x itself. So now by doing this, watch what we're getting. That's where the identity is coming from. It means now we have the following. Ax minus. Instead of 7x, I'm going to substitute it by 7 times the identity equal to x. We're almost at the end of it. So we need to show that ax equals 7x has a non-zero solution. Means we have to show that ax minus 7x equal to 0 has a non-zero solution. So it means we have to show that ax minus this equal to 0 has non-zero solution. Now I can factor out the x because I'm going to be working with matrices. But now how I'm going to factor my x? This is my a minus. I don't have 7 anymore. I have 7 times the identity equal to 0. So now I created a situation where I'm subtracting two matrices from each other, which is allowed. So showing that this has a non-zero solution is really boiling down to solving that this has a non-zero solution. Okay, now I have to combine a lot of ideas. Again, I have to ask you questions. Suppose I have a matrix C. C is n by n. Matrix. If the system C times x equal to 0 has a non-zero solution, non-zero, it means, what can we say about the matrix C? Invertible or not invertible? If you have matrix C, if Cx equal to 0 has a non-zero solution, means my matrix C, is it invertible or not invertible quickly? Invertible, not invertible. Right? That's a right. Okay, why? Because we have a non-zero solution. If it's invertible, if the matrix is invertible, then Cx equal to 0 will have only a unique solution because I will be able to multiply by C inverse. I cannot do that. So it means my C is not invertible. If a matrix is not invertible, what can we say about its determinant? That's one of the key ideas we study determinant in this class. If a matrix is not invertible, it means the determinant equal to 0. And now let me combine all those ideas right there. So to show that lambda is an eigenvalue, it means I have to show that there exists in X, a non-zero X such that Ax equals 7X. Now I'm going to solve for that. I'm going to find this X, but let's see. The question is, can I do that? So Ax equals 7X is non-zero is equivalent to show that A minus this times X has a non-zero solution. But it's equivalent to say that A is not invertible. That's what it means. Because the lack of invertibility will make this have a non-zero solution. It means, but this is occur if the determinant of A minus 7 is equal to 0. So let me sum up. 7 is an eigenvalue if this equation has a non-zero solution, which is this occur if and only if the determinant of A minus 7I2 equal to 0. Because if this determinant is 0, it means this matrix not invertible. It means this homogeneous system has a non-zero solution. By writing back, it means I can find non-zero solution for Ax equals 7X. So now let's write this down clearly here. Let me summarize what we said. So lambda equal to 7 is an eigenvalue for A, is an eigenvalue if the system A minus times X equal to 0 has a non-zero solution. Which occur when the determinant of A minus 7I is equal to 0. So let me sum up. So lambda equals 7 is an eigenvalue if I can find a non-zero solution for that. But when can I find a non-zero? I can find a non-zero when the determinant is equal to 0. So let's check the case. So now let us check. We're going to check. Let's check if the determinant of A minus 7I is equal to 0. If this occurs, I am done. I can find a non-zero solution. Okay, so let's do that now. Let's do that. So this is my matrix A. And we're going to find the determinant of A minus 7I and check if it's 0. Now, what is A minus 7I? Let us compute this matrix A. So what is A minus 7I? It's equal to A is 1, 5, 6, 2 minus. What is 7I? It means 7 times I is the identity 1, 0, 0, 1. So it's equal to now 1, 6, 5, 2 minus 7 multiplying it is just basically multiplying by 7 across, which is equal to. Now let's see how we take those away from each other. 1 minus 7. So I'm going to take 7 from 1 minus 6. 6 minus 0 remains 6. 5 minus 0 remains 5. And 2 minus 7, 2 minus 7, which is going to give me minus 5. That's the determinant. That's A minus. So now let's compute the determinant. So I know it's a lot, but it's actually not hard at all. Okay, we're going to compute the determinant. So that's a 2 by 2 matrix. It's minus 6 times minus 5 minus 6 times 5, which is 30 minus 30, it's equal to 0. So since the determinant is equal to 0, it means lambda equal to 7 is an eigenvalue. Right? What does this mean now? So that's question A, it is an eigenvalue. So let me back you up. If this is equal to 0, it means basically this matrix, this whole matrix is not invertible. It means if I take this matrix times it by x equals 0, I have a non-zero solution. If I rewrite that, it means I can find x, which is not 0, such that ax equals 7x. So having this determinant equal to 0 will allow me to find the x, such that ax equals 7x. So now my second question is, find the x. Find this non-zero x such that ax equal to 7x. So question number 2 now is the following. Find the eigenvector, find the eigenvectors that correspond to the eigenvalue lambda equal to 7. Okay. Having a 0 determinant tells me that we should be able to find an x such that ax equal lambda x. So let us understand what do I mean by that. But this is equivalent. Find the eigenvector that corresponds to eigenvalue lambda equal to 7. It means we need to find x non-zero such that ax equals 7x. That's really what it means. But now this is equivalent to solve the following. So ax equals something that's equivalent to solve the following system. A times x equal to 0. So lambda equal to 7 is an eigenvalue. Basically tells me that I can find a non-zero solution for ax equals 7x. But as we did before, solving this is really boiling down to solving that. And now this is what we're going to solve. So let us solve a minus 7x equal to 0. Now I'm going to take my matrix A minus 7i, that's the system I'm going to solve, 0, equal to. Now, a minus 7i, we computed it here. It's minus 6, 5 minus 5. Minus 6, 5 minus 5. Now watch. The determinant of this matrix is 0. It means when I solve, I will find a non-zero solution. To find a non-zero solution, it means when I'm going to solve that, I have to have a free variable. Otherwise, 0 will be the unique solution. And this cannot occur with a 0 determinant. So when I'm solving here, I should have free variable. I don't get free variable, it means I'm doing something wrong. So let us reduce this. Now, if I am doing this problem, I divide by 6. Here, I divide by 1, because this will make the problem much easier. Divide by 6 and divide by 5, because we want to deal with 6 and 5. And then I will proceed and go to my echelon form. So this is going to give me equal to. I can add both columns to each other, sorry, both rows, 0, 0. If I don't get something where there is a free variable, something is not right, because this is a matrix whose determinant is 0. It means that this matrix represents a system, that's the A minus 7i, such that this homogeneous system will have a non-zero solution. So now we get x3 free, sorry, x2 free. And if I solve here, I will get minus x1 plus x2 equal to 0, it means x1 equal to x2. And now we have to write the solution in parametric vector form because I'm looking for the vector x. So I need to write them in vector form. So I'm going to set this is equal to t. And this would become, of course, equal to t. So x will become. So we write in parametric form. And you get x equal t times 1, 1. What does it mean? It means that the eigenvectors that correspond to lambda equal to 7 are all vectors of the form t times 1, 1. Means all the scalar multiple of those vectors, where t is any number different from 0. Because eigenvectors, by definition, are non-zero vectors. So I have to remove that from 0. Okay? So the question is, so we have a lot of eigenvectors. Every scalar multiple of 1, 1 is an eigenvector. So one eigenvector would be one special eigenvector. If you want only one of them is 1, 1. That's one of them. If I want only one. If I want all of them, all scalar multiple of 1. Now, let's check. So let me combine. Let's check our work. Okay. What does it mean to check our work? I know that it's the beginning and it's a bit jumble mumble a little bit in your head, but let me connect the dot. What does mean that 1, 1 is an eigenvectors with eigenvalue lambda equal to 7? Mean that if I take the vector A and multiply it by 1, 1, I should get, check, it means that if I take A, I should get 7 times 1, 1. Not only 1, 1. If I take 2, 2, I should get 7 times 2, 2. So what does this mean? This is an eigenvector that corresponds to lambda equal to 7. Mean that if I take the matrix A and multiply it by this vector, it's going to be stretched by a factor of 7. That's really what it means. It means those vectors 1, 1, the way A act on them is by stretching them by a factor of 7. Let us make sure that this is correct. So let us see. Let me take A and multiply it by 1, 1. And let's see what I get. I should get 7 times 1, 1. Now A was 1, 6, 5, 2. So this is 1, 6, 5, and 2. I'm going to multiply it by that. I'm going to get 1 plus 6, that's a 7. 5 plus 2, that's a 7. This is equal to, I can honestly factor out 7 times 1, 1. So it's not really easy to find the vector 1, 1. That it's not easy to find this vector that A will stretch, but this is telling me that it's actually 1, 1 is an eigenvector with the eigenvalue lambda equal to 7. Okay. So in this problem, I did the following. I gave you a matrix and I took its particular value lambda equal to 7 and I gave it to you and I told you show that this is an eigenvalue. So the question is, how can you find those eigenvalues without me giving them to you? And that's what we're gonna call the eigenvectors eigenvalue problem. So in this problem, I did 2. In the first exercise, I gave you the eigenvectors. I told you check it's an eigenvector, which was easy. This was harder. I gave you a value of lambda. I tell you show that it is an eigenvalue. And we did a lot of work to be able to do that. The third part is I'm going to give you a matrix and I'm going to ask you find the eigenvalues. It means find this. To be able to get that, I have to basically repeat what I did, but in a more general way. So now my question is the following. How to find, not how to check, how to find the eigenvalues yourself without me interfering, slash eigenvectors. Okay, all right, it's not hard, actually it's simple. And let us see how we're gonna do that. Now, lambda is an eigenvalue if ax equal lambda x has a non-zero solution. Okay, now ax equal lambda x has a non-zero solution. That is, if the following system, what I did before for 7, I'm gonna repeat it for that. It means I'm gonna move the lambda x from this side. I'm gonna move the lambda x to the left and multiply it by the identity so I can subtract matrices. So that is, if this system has a non-zero solution. And now I'm going to use the same argument. This system has a non-zero solution, that's an n by n system, if the determinant of a minus lambda I is equal to 0. And using the idea of determinant, this occurs when the determinant of this matrix is equal to 0. Because if this has a non-zero solution, it means a minus lambda I is not invertible. Not invertible means its determinant is equal to 0. So lambda is an eigenvalue. If this occurs, it means if the determinant of a minus lambda I equal to 0. So now how to find them? So to find the eigenvalues, we set the determinant of a minus lambda I equal to 0 and solve for lambda. Okay, so to find the eigenvalues, I set the determinant of a minus lambda equal to 0 and solve for lambda. If I find the lambda such that this will occur, this lambda will guarantee that this system has a non-zero solution. This will guarantee that ax equal lambda x has a non-zero solution. So to find the eigenvalue, we look for all the lambda that make the determinant equal to 0. To find the eigenvectors, we solve this homogeneous system. So we solve this homogeneous system because when we solve it, we find the axis such that ax equal lambda x. And now we're just gonna take up a problem and do the whole picture. So here is our example. So please, guys, if you need the paper back, let me know, because if you don't, I will just move on. So this is now our last example, which with the whole picture, actually. I'm going to take A to be the following matrix. 1, 3, minus 1, 5. Okay. Question. Number A is find the eigenvalues. Okay, all right. How we do that? We're gonna set the determinant of A minus lambda I equal to 0 and solve for lambda. Okay, let's do that. First, let us compute. We have to get into the habit of computing that. What's A minus lambda I? It's 1, 3, minus 1, 5, minus lambda times 1, 0, 0, 1. Okay? Now that's equal to what? Right. It's 1 minus lambda. So basically, I took lambda away from 1. Minus 1 minus 0, I'm actually not touching that. And then 3 minus 0 and 5 minus lambda. Okay, so when I take A minus lambda I, what I'm doing is basically, actually, we're taking lambda from the terms along the diagonal, but those are not being touched because we're taking 0 away from them. Now I have to compute the determinant, set it equal to 0, and solve for lambda. So let us compute the determinant. Equal to 1 minus lambda 3 minus 1, 5 minus lambda. Okay, this is equal to. So that's it 2 by 2. So it's 1 minus lambda, 5 minus lambda, minus minus plus 3. Now, remember, we have to set this equal to 0 and solve for lambda. So when I'm setting it this equal to 0, actually what I'm going to get just a quadratic equation. So basically, I'm going to set this equal to 0 and solve for lambda. Now, if you look at it very carefully, this is going to give me quadratic because lambda going to give me lambda square. So let us multiply it. So it's going to give me lambda square minus lambda minus 5 lambda. This will give me minus 6 lambda plus 5 plus 3. So this will give me lambda square minus 6 lambda plus 8. So that's the determinant. Now I need to set this equal to 0 and solve. All right, remember I set, so here we're going to set equal to 0 and solve. And this is a simple quadratic equation. If I want to set equal to 0, so we try to factor it. And I picked something that we can factor easily, 2 and 4, lambda and lambda, and minus, minus. Okay, remember now I am solving. So this is going to give me lambda square, minus 4 lambda, minus 6 lambda, minus minus plus 8. So this is going to give me lambda equal to 2 and lambda equal to 4. So I have 2 eigenvalues. It means I basically have some vectors that A will stretch by a factor of 2, and I will have a bunch of vectors that A will stretch by a factor of 4. So these are the eigenvalues. So the eigenvalues are lambda equal to lambda equal to 4. Now, the second question is, for each of those eigenvalues, find the eigenvectors that correspond to them. It means for lambda equal to 2, I need to find all the x's such that A is stretched by a factor of 2. And for lambda equal to 4, I need to find all the x's that A is stretched by a factor of 4. So that's what it means, find the eigenvectors. So question number 2 is, find the eigenvectors, that correspond to lambda equal to 2. So for each one of them, I'm going to do that. All right, how to find the eigenvectors? Find the eigenvectors, basically, I need to find all the x's such that AX equal 2 times x. That's really what I need to find. But solving this is actually kind of hard, so we rewrote it as the following homogeneous system. So instead of solving that, we're actually solving this. So find the eigenvector that corresponds. So here we need to solve the system A minus 2ix equal to 0. In parentheses, which is equivalent to solve ax equal to x. And we should be able to find non-zero solution. Otherwise, everything we're doing is not correct. Something is wrong. All right, so let us solve it. What is a minus 2I? So first I compute a minus 2I. It's equal to. So the identity. And my a, I get my a back is 1, 3 minus 1, 5. And this is going to be equal to 1 minus 2 minus 1 minus 1, 3, 5 minus 2, which is going to give me 3. Now we solve. A minus 2 times the identity and the 0 vector, which is equal to minus 1, 3, and 3. And that's 0 and 0. Now I need to solve that. Of course, if it's easy, we just have to multiply the first row by 3, and so that's going to give me 3, 3, 0. And the first one multiplied by 1, we're going to get that. Immediately, we're having a free variable because we need a non-zero solution. All right, so definitely here, x3 is free, sorry, x2 is free because my vector here are in R2, and x1 is minus x2. So in vector form, so if I set this to be equal to t, this would be minus t. So in parametric vector form, x is t times minus 1, 1. Okay, so the eigenvectors that correspond, what t is t different from this? So the eigenvectors that correspond to lambda equal 2 are all vector of the form all the vectors of the following form: a scalar t times minus 1, 1 with t non-zero. Okay, these are the eigenvectors. So graphically, it means here we are. I am in R2, and this is the vector minus 1, 1. That's the vector minus 1, 1. Okay, and this tells me that every vector, which is a scalar multiple of minus 1, 1, means every vector on this line, no matter which vector I take, if I take this vector x and I compute a times x, I should get 2x. So it means this is my vector x. What a will do to it is just stretch it by a factor of 2. That's a times x. It's not only minus 1, 1. Any vector on this line, that we're going to give it a name, this line next time, any vector on this line, what a will do to it is just stretch it by a factor of 2. That's what a does to every vector on this line. Now, we have 2 eigenvalues, so we have different eigenvectors. So the last question is, find the eigenvector that correspond to lambda equal. So we had 2 eigenvalues, lambda equal 2 and lambda equal to 4. Now we're going to find those that correspond to lambda equal to 4, which is basically the same ideas now. There is nothing really hard anymore. So now the question is, find the eigenvectors that correspond to lambda equal to 4. That correspond to lambda equal to 4. Again, we need to solve this time. A minus 4i x equal to 0. And in parentheses here, I'm always trying to remind you that this is equivalent to solve ax equal 4x. That's really what we're trying to find. So solving that is basically the same thing as solving the system. So again, I will have to take a minus 4i. I have to compute it first. And then I proceed. So my a was 1 minus 135. I'm going to take it minus 1, 0, 0, 1. And 1 minus 4 minus 3 minus 1, 3 minus 0, that's a 3, 5 minus 4. No, sorry. 5 minus 4 plus 1. Okay, and now we solve. We take a minus 4i, and now I am solving this homogeneous system. That's the system I'm trying to do. And this is equal to minus 1, 3, 1, 0, 0. Again, echelon 4. Minus 3 plus 3 is 0. Minus 1 plus 1 is 0, 0. I can multiply the top by 1, and I get that. I have to have free variable. I repeat for the umpteenth times. So this is going to give me x2 is free. And x1, we have to be careful here. This would read 3x1 plus x2 equal to 0. So be very careful when you're reading. So it means that this is going to give me x1 is minus a third x2. So if I set this equal to t, this is going to give me minus a third t. So in vector notation, every eigenvector will have the form t times minus a third and a 1. So the t is different from 0. So the eigenvectors are all scalar multiple, are all vectors of the form minus a third 1 times a scalar, where my scalar is non-zero because by definition eigenvectors are non-zero vectors. Okay? Now we can actually check that my vectors make sense. So what do I mean by check? If I take A and let me multiply it by any vector of this form, I should get 4 times this. So I pick anything from this form. And I'll convince you that this is 4 times this vector. So let's do that. So this is equal to, t is a constant, I can move it, a times minus 1/3 and 1. So it's equal to t times. So I'm just checking that I'm actually stretching those vectors. Minus a third 1, and my original matrix was 1, minus 1, 3, and 5. And now I multiply. And if I don't get 4 times this, I'm in trouble. All right. Minus a third minus 1, minus 4/3. Minus 1 plus 5, 4. I can factor out my 4. I will get 4t, and this will give me minus a third and 1. That's my eigenvalue. That's the 4, and this is my vector. So if I take any vector of this form, what A will do to it is stretch it by a factor of 4. It's 4 times this vector. This is how we check that what our answers really make sense. Are they correct? All right, so I definitely stop at this stage. A lot of questions. The exams will be graded tomorrow morning. You guys will have your grade on Brightspace. All right, I think I'm almost done. So tomorrow morning at the latest, you will have your grade. Now another student wants a quiz on Wednesday. So we will have a quiz on Wednesday. Okay, it will be an easy quiz. The reason is I want to make sure you guys study this material. I cannot really, you have to study it. You have to know this material very well. So you guys will have a quiz on Wednesday. When will I haven't looked at the final exam yet. So let me look at that, Chris. Okay. So you will have a quiz on Wednesday, which will cover the two things we did today, a coordinate with respect to a basis and eigenvalues and eigenvectors. So I strongly encourage you to do the homework. Any other questions?
I have a question.
Please go ahead.
What is homework for in the grade book?
Oh, it's a mistake. I'm figuring out Brightspace to cancel it.
Okay, sorry, that's what I thought. I just wanted to make sure.
Yeah, you're right. You're right. Brightspace, it's a little bit new to us, so I have to figure out how to cancel it without canceling your other grades. So I'm looking up the literature.
Anything no worries. I was just making sure.
Yeah. Anything else? Okay. So see you on Wednesday. Bye-bye, guys.